Okay, great. So we did a problem like this on Wednesday last week. And so here's our beaker. We've got some water in it. And this is 200 grams of H2O. And I believe it's at 20 degrees C. Okay. Then we have an ice cube. And ice cubes are not blue. The water's obviously blue, right? And let's think for a minute about how this is similar to the problem that we did last time, and also how it's different. So this ice cube is 20 grams of ice at 0 degrees. So the question is, we're going to take this and we're going to add it to the water, and we want to see what we get as a result. All right, so the basic idea with calorimetry problems is that we're going to take the cube for the cold stuff and add it to the cube for the hot stuff. And a simple conservation of energy shows that that should be equal to 0 when we add the two together. Now, one's going to gain heat, and the other one's going to lose. So in this case, the hot, it's not really that hot. But, so this is going to lose, and this is going to gain. And that's the only way two things can add up to equal 0 is one of them has to be negative. So this is going to be a loss. When we do MC delta T for this, we know that the delta T is going to be a negative number. So that's where the minus sign is going to come from. And I'm just mentioning this because when we do the Q for the cold stuff, it's actually a little more complicated because we're going to have a phase change, and then we're also going to have a temperature change. So for the ice, we have two terms. We have M, L, F for the latent heat of fusion. And then we have an MC delta T. And like I said, all this is for the ice. Because if the ice melts, then we're going to have liquid water again, but we're going to have cold liquid water. The water's only going to be 0 degrees. And so whatever this final equilibrium temperature is going to be, that cold water is going to have to warm up, and that's where this MC delta T comes from. So the C that we're going to use here is for liquid water, not for ice. That's important. You're going to have something very similar to this on the quiz, which would be on Wednesday. So I don't want you to freak out about your first quiz. I just want you to make sure you can get all your practice work done. You've had a chance to ask a lot of questions. You do a little bit of studying, and then when you come in, you can bring all your notes with you. So just be as prepared as possible, but we are going to approach it in a collaborative manner. For the water, well, that's going to have an MC delta T. And that's going to be equal to 0. So the delta T for the ice, after it finishes melting, ooh, I don't know how well the green shows up. It's not look like it's going to show purple. Let's try purple. So remember, when you do a delta, you always do final minus initial. And it's the final temperature, I don't know. But the initial temperature of this melted ice is going to be 0. And then over here, delta T is going to be equal to whatever the final temperature is, minus 20. And that's where the minus sign comes from that makes this a loss. All right, I'd like you to go ahead and try and finish this. And just a quick reminder. So this is 20 grams, that's 0.02 kilograms. You might want to just take a minute and just jot that way underneath. So 0.02 kilograms. And the latent heat of fusion for water is 333 kilojoules per kilogram. And then we have ice that melts. And so that, again, that's 0.02. And the specific heat, we have to have it in units that match up with the heat of fusion, which is in kilojoules. So this is going to be 4.186 kilojoules per kilogram per degree C. In delta T, we already talked about. And then this is 200 and 4.186 again, and TF minus 20. Okay, well, I'd like you to try and carry it from here and see how you do. So ask questions by all means. Use the chat feature if you want to.
Sorry, did you say so we've got MLF, so M is 0.02 kilograms, and the latent heat 383 kilojoules per kilogram.
This one?
Yeah.
Or, yeah, this is latent heat of fusion.
Oh, that's what I meant, sorry. So 383 kilojoules per kilogram.
383 or 333?
I guess I didn't hear right, probably. Was it 333? I said 380.
Yeah. Okay.
Sorry.
No, it's okay. Let's see. I just want to show you where to look in the slide deck. So we often are going to refer to some of the tables that are in the slide deck. So that might be something that you want to have handy. All right, and I'll pull it up here in just a second. Okay. Right, so if you're taking a look at my screen, this is the thing I was warning people about, this kilojoules per kilogram, because the other table is just in joules per kilogram. So I'm sure that the textbook did it to save space, but that mix-up could definitely cost you. So 333 kilojoules per kilogram. And you're looking for TF. So feel free to put a number in the chat if you think you got it. Well, we have a first guest. Do we hear a second? Do we have a confirmation?
I'll agree with her.
Thanks, Brendan.
I moved my webcam, so I have no idea where I'm looking. So I'm like looking up there at my monitor, but my webcam's like underneath it. So
Yeah, a lot of the social graces are out right now. Okay, yes. So I would agree 11 degrees. So the temperature went down by about 9 degrees altogether, which sounds great. Now, before we move on from this, I just want to throw out a little warning there. What would happen? Because remember, the question is, what's the final temperature? What would happen if we had an ice cube that was 3 times the size of that? So what if the ice cube, instead of being only 20 grams, was like 60, or even, let's call it 100? What if it was 100 grams of ice that we added to 200 grams of water? And this is actually, you know, when we think about adding ice to something, it was a hot summer day, you want a nice cool glass of lemonade, you'd pack as much ice in there as you could. Right? So let's just think about that for a second. We know that 20 grams of ice cooled it off by 9 degrees. So now if we threw in an ice cube that was 100 grams, what would the final temperature be? And I'm going to go ahead and set that up. So if you, I am recording this, you could always go back and look, but I'm going to erase this. So if you do want to take a screenshot of it, feel free. Okay, so 3, 2, 1. So what's new is we're going to put a 0 here. And the final temperature is going to be 0. Because with your lemonade, why did you want to pack all that ice into your lemonades? Because you wanted it to be really cold, right? And so you wanted to have enough ice left over. Because once the ice is all melted, then your drink is going to start to warm up. So you wanted it to continue to be cold for some time. And in order to make that happen, then you're going to want to have that ice stay there for a while. So how do you know that the final temperature is going to be 0? Because if I actually tried to do the math on this, I'd wind up getting a negative temperature, which doesn't make any sense. And the way you would know is this. So ice, wow, he's making a big deal about this. Yeah, because like, quiz coming up, and oh, maybe there's going to be a question like this. Just maybe. All right. If I'm, I said 200, that's a lot, actually. Let's make it 100, because equal parts of ice and water is probably, it's pretty obvious it's all going to wind up at 0 degrees. But so with 100 grams, MLB for the ice is going to look like this, or MLF rather. So that's going to be 0.1 kilograms times 333 kilojoules. So that's going to be 33.3 kilojoules. And we come over here to the water and try to figure out what would be, if the final temperature is in fact 0, then how much heat is that? So that's going to be 0.2 kilograms times 4.186 kilojoules. And then the temperature change, if it goes from 20 degrees down to 0, the temperature change is going to be negative 20. Okay, so let's do the math out and see how that comes out. So that's negative 16.7. kilojoules. Right, so when we take a look at this, this is how much heat is required to melt all the ice, but the water can only give up this much before it's at 0. And then they're at the same temperature and it can't offer up any more heat. So the water in cooling off doesn't have enough heat to actually melt all the ice. So final temperature is equal to 0 degrees Celsius, and that means that ice remains. And if the ice remains, how are we going to figure out how much remains? Well, now we're going to look for an M that's smaller than 100 grams. We want to find out how much actually melts. So we would set the mass times the heat of vaporization, which is 333 kilojoules. And we would set that equal to what the water has to give, which is 16.7. I don't really need to worry about the minus sign in this case. So I'm going to divide both sides by this and see what we get. And I get 0.0502. That's in kilograms. So 50.2 grams melts. And so about 50 grams remains, or 49.8 grams remains. So these calorimetry problems, if I wanted to make it a little bit more challenging, what I would do is probably do something like this, where there's a phase change involved, and in the heat exchange, there wasn't enough heat available to complete the phase change. So I just want you to think about that for a second. Do you have any questions? I went off the screen there, but it's 49.8. That's how much remains. All right, how you doing? Yep. Okay, any questions?
Not a question, but just a request.
Yeah.
The video of the whiteboard is a little blurry.
Oh, sorry.
Just try to. Oh no, that's not really an issue. But could you just try to make like the decimal point a little bit more clear? Because like between like the 33.3, like now I'm looking at it, it's easy to see, but like when you're writing, so like
Yeah.
it's just hard to keep track. But just that's my only request.
No, that's fine. That's really good feedback. Thank you. I was thinking about that too. So I will definitely, I'll go over them a couple of times. All right, well, that sounds great. Let's go ahead and take a look at some of the new information for tonight. And I'm going to change screens and then share my video. All right, I'm sharing my screen and I'm sharing the notes. I'm not going to do it in presentation mode. I'm going to keep it like this just for navigation purposes. Let me know if you can see the slides okay. Great. Okay, quick review as we're going to go down through it. So the key ideas here is we start off with a definition about what heat is, and then we looked at phase changes and temperature changes and how much heat's involved with that. And then tonight we're going to take a look at the new material, which is about how heat actually travels from one place to another. So we took a look at the kinetic theory and kinetic energy of Markowitz classic ideal gas law rationale, and went through some units, of course, and then talked about what heat is, and heat is a flow of energy. Now I'm going to slow down here because this was a real key idea. And if you weren't with us last time, I just want to underline this and highlight it and circle it and make a billboard out of it. So the internal energy, U, yeah, that's another way of expressing internal energy. So internal energy is the total amount of thermal energy contained in a given quantity of a material. So I made this point last time that, you know, if you want to think about it, that total internal energy is based on temperature, but it's also based on how much stuff there is. So if you dropped a tiny drop of boiling water on the back of your hand, you'd go, ah. But if you had dumped an entire pan full of boiling water on your hand, you're probably headed to the emergency room. And the reason for that is that the whole pot of boiling water has a lot more molecules that are all pretty hot. And remember, in heat exchange, there are energy sharing collisions. So there are lots of molecules available for those energy sharing collisions, and it's going to mess up your hand. The other thing too is to think about what the heat capacity is, and that's what this next slide is. That, you know, in the beginning when we talked about the ideal gas law, that we're just talking about monoatomic molecules zipping around in three-dimensional space, and they only have three different ways that they can have kinetic energy, which is along the X, Y, and Z planes. But now if you talk about a molecule, and especially something like water, now it can have kinetic energy in rotating about its own axis, or spinning, even vibrating, oscillating between atoms, and there are lots and lots of places to store this energy. So when you have lots and lots of buckets to store energy and you add a fixed amount of energy to it, if you have lots of places to store it, then the overall temperature doesn't increase as much. So that's why water has a high heat capacity, because it's got lots of buckets to store energy. And those buckets are called degrees of freedom. So water has lots and lots of degrees of freedom. So you can probably expect some kind of conceptual question about how is the number of degrees of freedom for molecular motion correlate to heat capacity. That's a big idea. And sure enough, the next slide is about specific heat. So specific heat means per kilogram. But when you multiply M times the specific heat, you actually get the heat capacity. So that's why it says heat capacity is MC. Okay, let's go a little bit faster. So calorimetry is an exchange. We just talked about that. And then latent heat, of course, this is a famous diagram. The big pink zone is to really underline the fact that there's a huge amount of energy associated with the heat of vaporization. And this is what drives our climate. And it's driving our climate in a crazy way. So if you've been watching the news and seen the wildfires, 10 years ago, we would just talk about wildfires and, maybe in the Rockies and then occasionally California. And now we're talking about all the Western states. So the total amount of area right now on fire is equal to the entire area of the state of New Jersey, which is absolutely crazy. All right, so we looked at some particular values. I made a big deal about the kilojoules. And then we talked briefly about why vaporization, for example, is a cooling process. And that's because in energy sharing collisions, it's possible for one molecule to experience a collision and gain enough kinetic energy to actually break the intermolecular forces that hold it as a liquid. And then off it goes into the vapor. But if that's the case, then the molecule that left had a higher than average amount of kinetic energy, which is not available for sharing anymore. So the vaporized molecules are in general taking away a higher than average kinetic energy. And that's how come vaporization is a cooling process, is that the molecule that left carried a higher than average amount of energy with it. So if it carried a higher than average amount, the average left behind is going to be diminished. Now, probably in a quiz situation, I'm not going to ask you about vaporization, but I might ask you about another phase change. Hint, hint, wink, wink, nudge, nudge. And now the new stuff. So that was a good review. The new stuff tonight is about how heat gets from one place to another. Heat transfer by conduction is very common. We use it all the time. And I mentioned before, it kind of goes to that notion about what it means to feel warm. I asked you to put your hands together, put your palms together last time and feel how warm they are. And really the only reason they feel warm is because they've stopped the heat that's naturally leaving your body, which for you sitting down comfortably, listening to this incredibly amazing lecture is about 200 watts total. You're just kicking it. You're just throwing 200 watts off. Now, some of you, I'm guessing, are maybe thinking about, well, it doesn't even have to be what your academic track is, but here in Vermont, there are lots of barns around. And some of the big dairy farms, they don't even have windows. They just like leave the sides down like all winter long. Because the cows are throwing off huge amounts of heat. And they, in fact, can just keep themselves warm. And that's what one of our little design activities is that we're going to take a mammal and we're going to take a look at if you were going to make a shelter for it to be outside and in the fall or winter months, that how big would the shelter have to be before? So, how big could it be and have their own body heat still keep it warm? So we'll talk about that in a little bit. All right, well, here's the basics then. For the first time, we see this Q over T, and that's power. But it's also rate of heat flow. So we have heat flowing across this, but what we're most concerned with is the rate at which heat leaves. This is kind of sad because I'll just give you an example. If you're renting an apartment, heaven forbid you have electric heat and have to pay for it because that's extremely expensive. But even here at my house at 116 Lamar Road, we have an oil tank, and the oil company just came and filled up the tank, and I had the furnace cleaned a little while ago. So that's great. So I have like $500 worth of fuel that got delivered. And I know that the next time the fuel gets delivered, well, we're going to be burning fuel from the tank, right? Where did that heat go? It just went out the walls of the house. That's it. So in the process of trying to keep our inside temperature at like 68, 70 degrees, and when outside it's like 15 or 20, the heat's just gone and we don't get it back. So anyway, yeah, this is going to be a recurring theme in this class, especially for the first couple of weeks, because for the past century, all humans have been doing as far as generating energy have just been burning stuff. That's it. That's the only way we've been getting energy, is just by burning stuff. It's only recently that we've started to develop energy by using some kind of reusable energy source. So that's, you know, it's, like I said, it's a little depressing, but we do have an opportunity to do something different about it. And we'll talk a little bit more about solar in a few minutes. But let's finish with this concept. K is for conductivity. So we're going to have more heat flow if it's a good conductor, and the good conductors tend to be metals because there's a definite connection between conducting electricity and conducting heat. And then cross-sectional area is the amount of area that's in contact. And then this temperature difference, well, that's what's driving the heat flow. So this heat flow is going to continue until the two are at the same temperature. So if you shut off your heat in the winter, yes, your house is going to cool down, but the rate of heat flow will actually get less as the temperature inside your home decreases. That's why it does make sense to turn down the heat if you have a programmable thermostat, to allow the temperature in your home to go lower when people are sleeping, and also go lower when people are out of the house and they're working, because it is going to slow the rate at which you simply waste heat. And here they are. Here are our thermal conductivities. So again, you can see that the metals are very good. And then these materials down here are not so good. But not so good at conducting means they're a good insulator. So air is an excellent insulator. But there is a slight issue with pockets of air. And polyurethane, yep, really good. Goose down, sure, all these things. Wool, but we have, and fiberglass. And it's kind of interesting because fiberglass is not at the bottom of the list, even though we know that that's most of what we insulate houses with. But fiberglass is relatively easy to manufacture. Cork is wood, and so if you had a cork insulated home, that would be very expensive. Not to mention the trees wouldn't be very happy. And of course, wool and goose down, they would be great to insulate the walls of your home. But again, the sheep and the geese would be really annoyed about that. So
it's funny because my old house, well, my house in Vermont was insulated, had corkboard as the main insulation until we changed the siding. So we did corkboard, wood to do a hard thing, and then fiberglass, and then like a normal insulation. So like my house was like incredibly insulated, but
yeah,
I never heard of cork insulation until they took off my old siding. So
isn't that crazy?
They did it in the 60s. My house was built in the 60s, so
yeah,
they were doing it.
Wow, that's cool. All right, good. Now here's an interesting thing. Speaking of insulation, that's a good transition, Brendan. So we talk about what an R value is. So R values refer to the insulating properties of different materials. But it integrates two concepts, how thick it is and what the conductivity is. And so you can see that
glass is not very good. But it can be improved with a double pane glass. And so I don't know, I should talk to an expert about this, but I have a sneaky suspicion about this, that windows that are sold and claim to have like a noble gas as a filler in between double pane windows, like super argon windows or whatever, that what we know about noble gases is they're hard to trap because they don't react with anything, and it's easy for them to permeate through to molecular structures. So I doubt that there's any argon left after a while. But anyway, brick. Yeah, well, 1960s is one thing, but in the 19th century, for some reason, people thought brick was a good insulator because they made their fireplaces out of brick. And, after the fire was out, then it would stay warm for a while. So let's put some brick in there. But actually, it's not a very good insulator at all. But fiberglass 4 inches is a pretty good insulator. Now, the interesting thing about R values is that they add. So if you wanted to double the insulation, then you can throw 8 inches of fiberglass, and now your R value is going to be 24. So what we're going to do, this is Pluto, and so this is my daughter's dog, 6 pounds of miniature poodle. And we're going to see if Pluto could last in a shelter that's outside in the middle of winter. Don't tell him that I was talking about this because he would be really annoyed. He doesn't do outside very well. He doesn't do snow at all. And he doesn't even like grass, really. Anyway, so thermal conduction, check. That's one of the ways that he goes from one place to another. Convection. So there's no formula associated with this. Sorry to disappoint you. But the key thing to know about convection, and this is something that usually people learn about at younger ages, is that it's gravity driven. So warm materials are less dense than colder materials, so the warm materials tend to rise. And if the warm materials leave a vacancy, then it can allow cooler materials to come in and get heated. So yes, a lot of home heaters work this way. And then pump the hot water through radiators that do the third form of heat conduction, which is radiation. But I did want to stop and just mention, this is sort of a caricature of flames, but we're used to seeing flames like this. And the reason why they have tips like this is because the warm air is rising. And then fresh oxygen is coming in from below. And it's gravity driven. So that means that in zero gravity, fire doesn't look like this at all. Fresh fuel, fresh oxygen has to diffuse its way through spent fuel in order to continue the combustion. So sorry, Sandra Bullock, movie Gravity, that fire, no, not a thing. And then finally, we come to heat transfer by radiation. And this is obviously super important. So the first, and we're going to look at two different forms of this heat transfer by radiation. So this first one is just by glowing objects. And glowing objects give off heat at a rate that's proportional to their temperature raised to the 4th degree. This temperature would be in degrees Kelvin. Some other things to think about is that what is the surface area that's being radiated at? So think about a wood stove. That works really well in this case. So we have the temperature inside the wood stove, again in degrees Kelvin. This is the surface area of the wood stove. And this is the Stefan Boltzmann constant, so shown below. And then this last one, E, is called the emissivity. And that's the number between 0 and 1. So this is why lots of wood stoves are painted black, is because that really helps them radiate heat. Something that's painted black is going to have an emissivity near 1, which is going to make it almost a perfect emitter. It also, if something's a perfect emitter, it's also a perfect receiver as well. So if you're, if you are out skiing or snowboarding this winter and you're thinking about what clothes you're going to wear, So if it's a nice sunny day, you probably want to put on black because it's going to help you stay warm. But if it's not a sunny day, you probably want to wear something light colored, something white, because that's going to cut down on the rate at which your body gives off heat to the environment. So this is for glowing objects, and it doesn't necessarily have to be like red hot glowing, it just be warm. Because when people put their hands up to the campfire and they put their palms towards the fire, what they're doing is they're picking up on the thermal radiation that's coming off the fire. It doesn't have to necessarily be emitting visible light either, because like a good wood stove is going to kick off tremendous amounts of infrared radiation. And then this is the last form of heat transfer by radiation, but we're going to actually spend the most time talking about this form because it has a direct relationship to solar power. So let's take a look at a couple of practice problems. I'll just throw out some details here. So this 1,000 watts per square meter, it's called the solar constant. That's what we get from the sun. 1,000 watts, 1 kilowatt per square meter, which is a lot of energy. Now, the area we're talking about is like if you slice the Earth in half and thought about sort of the cross-sectional area of it, that's the working area that we're talking about. And the emissivity, again, plays a big role in how much energy is received. And then cosine theta, well, that would be the angle the sun's coming in at. And the best angle that we get is at what's called solar noon. And at solar noon, the angle that we're talking about is essentially what latitude you're at. So for us, that's pretty close to 45 degrees. The Canadian border is like 44 and change, I think. Is that right? No. Wait, do you cross 45 when you get to the border? Anyway, kind of interesting. Halfway to the North Pole, which means two things. Is that it's cold here. The other thing it means is that the North Pole is still really far away. All right. Let's put this into practice. And we're going to take a look at how much your roof is worth. So I'm going to click here to our agenda. And we'll just take a look at a couple of things. Before we go too far, I did want to just share this video with you. This is going to open up. Let's see if it opens up in this tab. This is showing 40 years worth of satellite imagery of the polar ice cap at its minimum. I know this isn't a new story for you. The interesting thing to see is you can also see some glaciers here in the northern part of Russia. And I'm just going to pause this for a second after the graph comes up. So why is this related to heat transfer by radiation? And the answer is that if we take a look at the color difference here and here. So as far as emissivity, this is the rate at which the polar zone is going to absorb radiation from the sun. The emissivity here is almost zero. So that means it's not really receiving a lot. It's reflecting most of the energy from the sun. But the open water here has an emissivity that's very high, like around 0.8 or 0.9, something like that. So it's actually, it heats up very quickly under the influence of the sun. And that's part of the problem, is that in a feedback mechanism like this, solar energy and the average temperature of the Earth is increasing, so that's causing the ice caps to melt. But as they melt, it provides more open water, which also receives heat from the sun at a higher rate. So these are some of the big concerns about climate change, is that a lot of these are positive feedback mechanisms if they're not arrested. So positive feedback meaning that the thing that's causing the change contributes more to the change. And the issue with global emissions is that as more greenhouse gases are added to the atmosphere, it's added in addition to the ones that are already there. So climate change is, the temperature of the Earth is warming, but we continue adding the warming elements to the atmosphere. So we're accelerating the pace until we get to a point where we can have a neutral carbon footprint. All right, let's just go back and take a look at our syllabus then. The class does get have better news in it later on. I'm just, if tonight's been kind of a downer. All right, this is actually pretty good news. So we're going to take a look at what your roof is worth. And we're going to use something called insulation. So in the slide that I showed you before, I talked about the rate at which heat, the rate at which we get energy from the sun. But it doesn't take into account length of day, and it doesn't take into account weather, and it doesn't take into account what latitude you're at. But through computer simulation, we do actually have a pretty good idea of what that looks like. So, let's see, did I want to? Actually, let's take a look at 36 really quick, and we'll do this one together. So, before we move on to the other piece I wanted to do today. All right, why don't you jot down some of the specifics about this, and we're going to see how this thermal conduction equation works. So what do we know? We've got 200 watts, that's U, and 1.5 square meters, and a temperature difference of 0.5. We want to find out how thick something is. So I'm going to change my view. I'm going to stop sharing.
I'll leave that up for a minute so you can jot down specifics and why which select word. And Brendan, I'm going to give you the biggest decimal points you've ever seen.
I'm excited to see them.
Okay, so stop sharing and change video. Oh my gosh, it's dark out there. Okay. So here we go.
Humans. So essentially, I think we're talking about something like this. So we've got two different layers of the dermis, and the temperature difference is 0.5 degrees C. And so this is layer of skin. Now the heat that's crossing this boundary is 200 watts worth of heat. I referred to that earlier. So that's how much, just from your metabolic rate, you're just kicking off 200 watts. When you start to exercise, it bumps it up. And then just when it bumps it up, then this is the rate at which your skin can shed heat. But if you are generating more energy inside, then your body has to find a different way to regulate that temperature. Otherwise, your temperature is going to go up. And if you're exercising, this is kind of funny because the gyms would reopen, right? But if you went in there with a thermometer while everybody's exercising, you'd think everybody has the virus. So because their temperature is elevated. But that's where evaporation and sweating comes in to help regulate that temperature. All right. So what we want to do is find out what this thickness is. So Q over T is equal to K times A over L. I'm going to use a cursive L because capital L we use for latent heat. I don't want to confuse the two. And then we have a delta T. In the formula that I showed you in the notes, it was T1 and T2, but it really is just a temperature difference. All right, well, let's see if we can solve this. So we have 200 watts. That's Q over T. Remember, a watt is a joule per second. And so energy is measured in joules, time is measured in seconds. So this has units naturally joules per second, or watts. And so that's 200. And then that's equal to K over L. So the K value is in the table. And we can dial that up. A few slides ago. And as we go to take a look, we're talking about human tissue, and we want to be careful about the choice of units. So this is joules per second meters degrees C, kind of weird, but it's 0.2, which is not a very good insulator. So I'm not going to say anything about trying to insulate a home with human tissue, but it wouldn't be good. So 0.2. I'm not really going to worry about units too much. An area, 1.5 square meters. Don't ask me how that was measured. This is the total area of your skin, which, as you know, is the largest organ in your body, by your body. I don't know. But L is what you're trying to solve for. And then delta T is 0.5 degrees. Great. Okay, so if we multiply both sides by L, divide both sides by 200, we can see what we get. So go ahead and try that on your own. It would be great if you could share in the chat what you get. So we're using the SI system of units, which by default measures lengths in meters. And the expression about being thick-skinned is actually an accurate one. And based on evolution, wherever humans tended to adapt to their climate, they might have thin skin, which helps them shed heat, or they might have thick skin, which helps them keep heat, rather. Yes, so 3/4 of a millimeter. That's what the 7.5 times 10 to the minus 4 is. Nice work. Okay. So now I'd like to just do one example with you that is like good news, I think, and it has to do with solar energy.
I'm going to go and take a look at our syllabus. And 38, you can certainly do, but it takes more time, I think, than it's worth. But here are answers, so you can take a look at how to do those. And I wanted to get to these values. So these are called insolation values. You can see here's the word right here, insolation. Not a U, it's an O, insolation. And it's kilowatt hours per meter squared per day. The Roman numerals are months. And so these are monthly averages of the amount of energy that we get per square meter per day from the sun. So you can see in July and June, we're really kicking it. August starts to trail off a little bit. Here we are in September, and it's really starting to fall off. Just a little bit less than 4. But then look at this. This is 1.3. That's not great. So that's December. We know that the sun is leaving us right now, and it's almost at the equator. It's about to cross the equator and then hang out with the southern hemisphere for a little while. But what a big swing, you know? So the highest value we have is 5.37. And if I compare that to 1.32, that means that we only have 1/4 the total amount of solar energy in December than we do in June. Wait, did I say this was good news? All right, we're going to get there. So yeah, this is the insolation factor. And what we like to do is find out on a nice sunny day in the peak of summer, how much energy can we harvest? Because that's really what happens, is that we're harvesting energy from the sun with solar panels. So the question is, how much is your roof worth? So if we picked a roof and then we use these insulation factors, how much money could you be making? That seems like a reasonable question, right? All right. Now, these insolation factors are tabulated all over the world, and there are a lot of places in the US that are much better solar energy, but for some reason, Vermont has a really high per capita installation of solar panels. I guess we're just crazy. But it's not a bad thing, because once you install them, they just sit up there and they harvest energy, and it's not that worrisome, unless you get a hailstorm. So let's work with this, 5.37, and we'll pay attention to the units. Again, so I'm gonna take a look at my whiteboard again. And the question is, how much is your roof worth? Great, so you should still be able to see my whiteboard. Now this insulation value is taken into account the idea about an angle. So even though your roof might be have a certain pitch to it, they all do, of course. We could make a reasonable approximation of your roof and its surface area by just approximating it as the same as the floor plan. So let's suppose a modest floor plan has a square footage of 2,000 square feet. That's comfortable. It's not particularly large, but you know, it's a decent sized house. So that's our floor plan. It's 2,000 square feet. So the Q that we're talking about, this number, this insulation factor, is 5.37. Now we'll just try and break down those units a little bit more carefully. Kilowatt hours, I guess we have to figure out what that is, per square meter per day. So we probably want to convert square feet to meters.
So our area is equal to 2,000 square feet. And we want to multiply by a factor. So that gives us square meters. So I know that 1 meter is equal to 3.28 feet. But if I multiply that out, that's only going to give us one factor of feet. So I have to square it. So my new value is 186 square meters. Great. Now, what's this kilowatt hour thing? One kilowatt hour is a unit of energy. So that's equal to having 1,000 watts or 1,000 joules per second and having it on for an hour. And 1 hour is 3,600 seconds. So 1 kilowatt hour is actually equal to 3.6 million joules. Or we could also call it 3.6 megajoules. And joule is not a very big number. It's not a very big unit of energy. So in terms of your electricity bill, your utility bill, it's usually coming in on kilowatt hours. And 1 kilowatt hour costs, well, here we are in the United States, it's ridiculously low. Costs only about 12.5 cents. Europe is paying roughly twice that. So the incentives in Europe to add solar energy are a lot higher. And hydro and all sorts of other things. In fact, there's so much solar power now that sometimes there'll be a glut of solar energy on the grid. And so what some utilities are doing is they're actually using electrical energy during the peak sunlight hours and using that to drive pumps that pump water uphill to holding ponds so they can reuse hydro at night. There isn't any real big storage anywhere on our grid. So whatever's being consumed in the United States right now is simultaneously being produced. Energy is not stored anywhere. It's too expensive. Green Mountain Power would love to lease this thing called what's the latest version of it? So it's a big battery made by Tesla, and it just sits on a wall in your house, and it stores electrical energy. So Green Mountain Power was trying to do that because a lot of renewables, you can't really control the rate at which they're made. So they're trying to dump energy into people's homes and let people store the energy. And then at night, they'll drain it back off and feed the grid that way. All right, so we're almost there. We've got our area. And then per day, we've got a cost factor built in. So we're ready to do a little bit of math. So here we go. We're going to take 5.37 and we're going to include the units so we can see what's happening. Kilowatt hours per square meter per day. And then multiply it by the number of square meters we get. So this is 186 square meters. And those units will cancel out, and then I'll have kilowatt hours per day. And then if I multiply by this factor, dollars, 0.125, and that's the cost for 1 kilowatt hour. And that's about what the Canadians pay too. I think Canada is actually a little bit less because they have tons of hydropower. The hydropower that they're talking about is thousands of miles north of Montreal. So it is a challenge to pump it, to get the electricity from where it's being generated to where it's being used. But they're selling a whole bunch of it to New York City and to Boston, and going south. So let's see what this is. So the total, when we're all done, that's what your roof is worth. Per day, that's how much money your roof is worth per day if you were harvesting all the solar energy that's hitting it. And of course, this is mid-June. So I'll let you just go ahead and do this calculation on your own. And you tell me if that sounds like a good deal or a bad deal. Let's see what you get. This is per day. Nothing fancy, just straight out multiplying them out.
I don't know what I did, but I was way off.
Why? What do you get?
I forgot the 5 at the beginning. There was too much in between, and I got confused.
Yeah, no problem. You good now, though? Awesome.
Yes, I am.
Okay, so yes, you're all right. Everything that's coming through the chat, that's correct. $125 per day. Now, if you could make $125 a day without doing anything, how quick would you be to sign that contract? I think, yeah, right? That's amazing.
Pretty quick.
Yeah. So what's the deal then? What are the issues with this scenario?
Wouldn't you have a really high initial investment cost?
Yeah, that's definitely true. You'd have a really high investment. What else? Think emissivity.
Well, if you said think what?
Emissivity.
So that was the E factor. So if they're collecting this much energy, so they're going to put that much energy like on top of your house, right? So like it would heat up your house essentially.
Yeah, it does actually. That's why the shingles are so hot. It's because they're actually pretty good at absorbing that energy. And then the question is, if we're trying to convert them into electricity through solar panels. And so the big issue is that, and it has somewhat to do with emissivity, but solar panels are not 100% efficient. So that's why. In the early stages, the solar panels were only about 5% efficient. Right, so 5% of $125 is like, I don't know, compared to the initial investment, like Riley said. So right now the target is for like 30%. If we can hit 30% efficiency, then you're going to see everybody switching. Even Exxon will switch to solar power if we hit 30% efficiency. And it would make sense for all our energy companies to really start thinking about battery technology and solar panels. Because right now, the Chinese are outproducing the US in solar panels by a factor of 2 to 1, which is crazy. You would think we would be the leaders in that, but that's not true. It's not happening. And India is going to overtake us soon as well. So anyway, there's just a little insight. So right now, decent solar panels are coming in at around 20% efficiency. That's pretty good. So if you get the chance, and you're thinking about, you're on your career path and, you get that, first time you get that salary job, you're not working by the hour. Yeah, you can start thinking about what's next. But yeah, try and put solar power into your ideas. And a lot of folks think that within about 10 years that solar power is going to be the plurality of energy that's harvested in the world, which means that it would be the #1 source of energy within about 10 years. It's going to be solar power. Why not? I mean, it's just a complete no-brainer. All right. Well, let's take a 10-minute break and come back at 7:30, and then we'll see what we can do for Pluto's little winter shelter. Okay, see you in 10. Okay, Maddie, Riley, Layla, are we ready to go?
Ready to go.
I'm ready.
Cool, that's great. Thank you. All right. Let's go ahead and take a look at this shelter. So this is a document that is on Canvas. And this is my downloaded version of it. So I'm talking about a geodesic dome. So the reason for a dome is, number one, the math is easier. But I don't know if you've heard of Buckminster Fuller, but he was someone who was talking about the human impact on natural resources and climate in the 40s, which is really amazing. He was way ahead of his time. And started talking about how we can rethink the way we use natural resources. Now, clearly, it was an uphill battle for him to get people to pay attention, because we're still having a problem with it now. Hopefully, your generation can do something a little bit better. I'm technically a baby boomer, and boomer, you guys didn't do such a great job. But Buckminster Fuller was looking at all sorts of interesting ways of conserving resources. And in particular, one idea of his that did sort of catch on for a little while was the idea about human shelters, instead of being rectangles with peaked roofs, is that what if they were sort of domes? And the reason for the dome shape is that it has the smallest surface area to volume ratio. So if you're thinking about making a shelter, you care about volume. But surface area, that's the stuff that costs money. So, that's the cost of the shelter itself. So if you can reduce the dollar cost, and also if it costs dollars, it costs natural resources too. So if you could reduce the ratio of natural resources per, how much shelter you get, then that would definitely be a more sustainable way of thinking about it. And so the triangles and trapezoids of these geodesic domes is a way to take linear materials and start to fit them together in something that approximates a dome. So in this picture, I have it from the other class that this is an alpaca, not a llama. And these alpacas, and there's a baby one, have a winter shelter that's shaped as a dome. Now it doesn't look very insulated, but they throw off a pretty good chunk of heat, just body heat. And so if they're in the shelter and this shelter can trap their body heat, then they can have a more comfortable temperature than if they're just outside of the dome. So that's our question right here. And is, can an animal's own metabolism generate heat to provide a comfortable interior temperature when the outer temperature is a chilly 0 degrees Fahrenheit? All right, so what do we do? How do we start? Well, it says, let's come up with the numbers that would represent a geodesic shelter for your favorite furry friend. Is it going to be big enough? And one measure of how big it is going to be how much square feet is available for movement. So that would be floor square footage. And there's a quick note here is that Building Energy Code in Vermont recommends R49 for ceilings and R13 for exterior walls. So the R value that you pick should be somewhere in between those two. Now, I'm going to do an example calculation for you that features a 6-pound miniature poodle and R49. So I'm going to go with the extremes. Lots of insulation, very small body mass. And the reason for doing that is that when we think about the metabolic rate of animals, that it's not exactly proportional, but it's roughly proportional to how much mass there is. So the bigger the animal, the more heat they're going to throw off. We can see a little bit more about that by taking a look at, I just want to make sure, yeah. I intended to share screen when I was doing that, so here we go. All right, good. Are we seeing that document? Okay, thank you. Now, there was a formula on the agenda that said basal metabolic rate from mammals, BMR, is going to be this coefficient, which is A times the mass raised to the 3/4 power. So I'm just going to jot that down for a dog. So it's 0.37. So I'm going to take that, that's the A value, and I'm going to multiply it by the mass raised to the 0.75 power. And then I want to see how big a shelter we can wind up with. So I'm going to switch, I just jotted that down. And again, I said that the poodle is 6 pounds. So I'm going to open up a tab on my browser here, and I'm just going to say convert 6 pounds to, and that's 2.72. Now, hopefully, you know, as you're thinking about this, you can start kind of brainstorming what animal would be interesting for you to do. So dogs, cows, something like that. And then you can sort of, you know, just ask the internet what the average weight is of an adult, whatever, or maybe you're raising babies, or I don't know. So anyway, these are all things that are sort of up to you, up to your choice. And I'd like you to try and do this in such a way that if you have a nice clean piece of paper, that you could sort of walk through the calculations that I'm going to do as an example. All right. And like I said, I'm going to go extreme, so I'm going to choose an R value of 49. But that's expensive. So that makes sense. Everything about this poodle is expensive. But if you're thinking about a cow, maybe you're, you know, and you want to go on the cheap, then maybe you think about like an R13 or something like that. Okay. So here we go. Stop sharing. And go back to the whiteboard. Yeah, so I'm going to take about 5 minutes to walk through this example, and then when you do yours, you can just take a picture of it and email it to me. That's fine. And I recommended last time, and thank you for those of you that have shared the practice work with me, that if you have a scanning app on your phone that can make it a little bit clearer picture when you go to take a, use your phone to take a picture of a piece of paper with writing on it. Let's talk. Okay, so we're going to start off with this idea about heat loss through radiation. And we said it's K times A over L, where L is the thickness of whatever cross-sectional area is transmitting this radiation, and then delta T. Now I can rewrite that to incorporate the R values, because R is L over K. If you increase L, you get less thermal conductivity. And if you reduce K, then you get less thermal transmission. Those are all important to be more efficient. So for the sake of efficiency, we want to reduce this as much as possible. So the R value incorporates both of these. So both of these variables can get folded together into an R value. But K over L is not equal to R.
R is equal to the inverse of that. So this is going to, yeah, I can keep that sign in there. So this is going to be A over the R value times delta T. That makes that quite a bit easier. And what we're talking about is putting a dome, and then we're going to put Pluto in the dome. And he's just a little guy. I usually just draw stick figures, so I'm trying to think about what a dog looks like in stick figure land. Woof. I don't know, something like that. So the floor, the square footage is going to be equal to the area of a circle, so that's pi r squared. But the heat that's leaving is leaving through the surface of the dome, and that's what I'm going to try and insulate. So if I can cut down on how much heat's being radiated, then that's going to allow a higher temperature inside. You see, that's what happens. We're going to establish an equilibrium at some point. And this is what's being given off by your animal. And so if we can cut down on the rate at which, if we can cut down on this number, then this number will be bigger, a bigger temperature difference, which means it'll be warmer inside than it is outside. And my suggestion is that you do 0 degrees Fahrenheit, but I know this is not going to work for Pluto. So I'm going to assume that the outside temperature is 30 degrees Fahrenheit. And Pluto doesn't really do well with cold weather. So we're going to have to keep this at 70 degrees. Now, if you have like a llama or something like that, then this could be like 40. A llama would be pleased as punch to be in 40 degrees Fahrenheit. And a cow, yeah, I'm probably sure a cow would like 40, 50 degrees, totally happy. So these two are things that you can pick. I just know that these numbers are not going to work if this gets too much colder. I'm gonna pause for a second, check in with you because we're about to jump in. How's it going? Okay. All right. So all in my diagram, everything that's blue is your choice. So internal temperature, outside temperature, and your R value. I'm going to go with building code for ceilings. And it has some weird units here. It has some imperial units to actually make this work correctly. So it's pretty bizarre, but it turns out that when you plug all these units in, then the unit you get for Q over T is BTUs per hour. I know, it's super weird. So we're going to keep imperial units, which means feet and hours and BTUs. Excellent. So let's start off with the BMR for Pluto. So we have a dog. And it says A times M raised to the 0.75 power. So dogs are 0.37. And then the mass was 2.72 kilograms after I converted pounds into kilograms. And I'm going to raise that to the 0.75 power. And see what we get. And now let's take a look at the units.
I would recommend that you just try and do this on your calculator really quick so you make sure you're getting that raised to the 0.75 correct.
So I'm still sharing my screen, and I just wanted to share with you what the units look like for R values. So they're kind of crazy. It's feet squared times hours times degrees Fahrenheit per BTU. And then the number I just calculated has units of megajoules per kilogram per day. Kilograms to the 0.75 power. So I already took care of that. I put in kilograms. And so the units for this are megajoules per day. All right, so if you can still see my whiteboard, I've got 0.784, and that's megajoules per day. So that's how much this dog is throwing off. It's this many megajoules per day. But I need actually BTUs per hour. So I'm going to convert that. And I'll ask the internet to help me out with that. I want BTUs per hour. So let's see how Google does with that. Well, what do you know? It's not that helpful. So where are we? I'm going to get rid of my points. I guess we're just going to have to do it. There we go. Okay. Megajoules set. All right. It's not very helpful. All right. Let's just do megajoules to BTUs, and we'll do it that way. 784. Honestly. Come on, internet. Okay, 743. Great. Back we go to the whiteboard. Okay, and I've got per day. So now we can just do dimensional analysis to convert days to hours. So that means 1 day is 24 hours. So that's not too bad. So we're going to divide by 24 hours. Okay, and I give it about 31 BTUs per hour. Just going to pause for a second. See if you have any questions about that.
does the BTU per hour have like does it fall into like a different unit?
Yeah, right. So we're talking about a unit that's got energy over time. And a BTU is an energy unit. Remember, it's that silly the amount of heat required to heat 1 pound of water by 1 degree Fahrenheit.
Okay. Oh, yeah. Because I was just googling like random animals and what their basal metabolic rate was, and it keeps giving to me in W, and I don't know what W is.
Probably just watts.
Oh, great.
Yeah, so that would watt is a joule per second, and then converting joules per second into BTUs per hour. Okay, well, here we go. So if we do this pretty simple equation, right? Q over T, which is equal to A over R times delta T. And then plug in an Nurmson. Remember, this is BTUs per hour, so this is Q over T already. So that's going to be 31. And A is what I'm looking for, but A is the area for the dome. So the dome area.
Sorry, I couldn't quite hear you. Could you please repeat what you said?
So annoying. Okay.
Siri didn't like imperial units, the way I said it. Anyway, so the dome, I'm writing this kind of small. I'll write it right here so it's a little bit bigger. So the area for the dome, well, it's half a sphere, and the area of the sphere is 4 pi r squared. So for the dome, it's only half of that, 2 pi r squared. And I'm solving for r. Now, I already said I'm going to use R49, the most expensive insulation I could possibly find. And then delta T. My delta T is 70 minus 30, so that's 40 degrees Fahrenheit. But again, that's going to be choice, up to you, depending on what your animal is comfortable with. Your lawnmower probably doesn't want to be at 70 degrees. So that's the question. We want to see how much area we can allow if this much heat is going through it. Because if the area is bigger, then this will have to be smaller, a smaller temperature difference. Now, this winter, when it's starting to be like November and you really care about the heat situation, that's why you have to turn up the heat. It's because the temperature difference between inside and outside is bigger. And so you can't really change this in your house. So you have to turn up the heat in order to maintain that temperature difference. All right, so we're solving for area. And then whatever area I get is going to be in square feet. So the area I get, this is the area of the dome, which tells me how much insulation I'm going to have to buy. And so that's 2 pi r squared. Now we're still in imperial units, so whatever I get for an answer is going to come out to be in feet. So I multiply both sides by 49 and divide both sides by 40. And I get an area of 38 square feet. That's for the dome. Then I use 2 pi r squared, again 2 because it's half a sphere. So I divide both sides by 2 and I divide both sides by pi. And then I take the square root of that answer. And I get about 2.5 feet. And that's the radius. So the diameter is 5 feet. That's actually a pretty reasonable amount of space for this eminence. And then the floor area would just be half of what this is. So the little guy is going to have 19 square feet to prance around in. And that sounds reasonable. So what happens if instead of 30 degrees, it's 0 degrees? Well, in order to make this work, the dome's got to get smaller. What happens when you're talking about a llama that's coming in at maybe, I don't know, 150 kilograms, something like that, and you have a bigger temperature difference? Well, the issue is a llama's a lot bigger, so they're going to need a lot more floor space to be comfortable. But they can probably put up with a much lower temperature than this. So remember, the things that you have choice in are the things that are in blue. So you have choice about the animal, and then it's your choice about what insulation you want to use. In the past, I've had people calculate how much it's going to cost, but that's a little bit excessive, I think, for this. So you choose how much insulation you want to use, and you choose what the temperature difference is. And the temperature difference would be the difference between what the animal can tolerate reasonably and what the outside temperature is. And if I had done 0 degrees Fahrenheit for Pluto, then this thing would have shrank down to like, he can hardly turn around at all. So. All right. So I'm going to stay online. If you want to do this for homework, you can, but it's a little complicated. So I'm happy to just kind of be around, and you can, if you get any questions, you can hit me up, and I can also run numbers for you. I have a spreadsheet where I can just type stuff in and see if it works. Well, I'm going to stop recording, and then I'm going to post this to YouTube, and I'll put a link, and I'll do that all while